The study of logic is the study of principles of reasoning, and it looks like whether or not the reasoning we can give for certain claims to properly establish a conclusion actually works. So, for example, if I said Socrates is mortal, the job of the logician is basically to see whether or not we can derive that from the claim that Socrates is a man. So, the logician is basically concerned with whether or not the argument itself is a success. And an argument here is just going to refer to some chain of reasoning in support of some claim or conclusion. The conclusion in this example is that Socrates is more mortal, and the argument for such conclusion is that Socrates is a man. So in this case, we're going to say that the reasoning for the conclusion is that, Socrates is a man, and that the conclusion here is that Socrates is mortal. Now, first, we need to cover what the laws of logic is before we can actually go into arguments and how they work. So, firstly, we have the law of identity, that being something is identical to itself. So, like, for example, 1 equals 1, x equals x. Second, we have the law of non-contradiction, which is just that a statement cannot both be true and not true in the same sense. You can't have two mutually exclusive statements be true at the same time and in the same sense. For example, you can't say that John exists and that John doesn't exist at the same time and in the same way. And finally, we're going to have the law of excluded middle. Either a statement is true or it isn't true. There isn't a middle ground or halfway. Either a statement is true or false. So let's start with introducing arguments. So in logic, what we deal with would be specifically arguments. Now, not all arguments are going to be equal in this case. So let's take a look at this argument. The sky is blue, so that means all turtles are evil. Clearly, this argument fails. The reason why it fails is that the conclusion that the sky is blue doesn't actually follow from the reasoning. So in this case, the sky is blue is going to be a reason or premise, whereas the conclusion is just going to be that all turtles are evil. So the conclusion does not follow from the premise, and therefore the argument is a failure. It's a non sequitur. And a non sequitur is just going to refer to some conclusion that isn't derived properly by the argument. So in this case, it's a non sequitur to say that the turtles are evil because the sky is blue. That would be a non sequitur. The argument is therefore logically invalid, which just means that the conclusion doesn't follow. Now, on the contrary, logical validity refers to an argument where the conclusion does follow from the reasoning. So let's take this example. Well, let's go here. So let's take this example. If John is a philosopher, then he thinks. John is a philosopher, therefore John thinks. In this argument, the conclusion here is going to be that John thinks. And the two premises we're using is that one, John is a philosopher, and two, if John is a philosopher, then he thinks. So here, this argument is logically valid. The conclusion actually follows from the premises. Now, this argument is going to be what is called a modus ponens argument. So first you have the conditional, right? That if John studies, he will pass the test. Two, John studies, that's going to be the antecedent of the conditional. And then from there, you can derive the consequent. So right here, what I've highlighted is the conditional. What I've highlighted here now is going to be the antecedent, and this is going to be the consequent. So this argument structure is just going to be something that you're going to see generally. This is something that's universally applicable to any argument, that being modus ponens. You can use this with any set of premises and the argument will be logically valid. So now you can see we've substituted the original propositions, which is P and Q, as substitutes. And we can really just substitute P and Q with anything and the argument will be logically valid. Now, what you'll see is that we have P and Q. Now, P and Q represent any proposition, where proposition refers to basically something which declares a claim to be true. And this is going to be distinct from like two statements. So, for example, the statements, the sky is blue and the sky is blue, but like translated to Spanish, these are going to be two statements. And the underlying meaning of the two statements is going to be the proposition. So a proposition isn't necessarily identical to two statements or to any statement, but rather the proposition is the underlying meaning affirmed by the statements themselves. So in this case, whatever truth value is affirmed by the statements, the sky is blue or el cielo es azul, this underlying truth affirmed by that is going to be the proposition, not the actual like language or how we represent that in language itself. This is another structure of argument that's going to be a modus tollens. So the way this works is that you're going to have some conditional, right? And then you're going to deny the consequent. And then from there, you're going to deny the antecedent. So in this case, the conditional is going to be the first premise. And here the antecedent is going to be Abraham Lincoln was alive today. and the consequent is going to be Abraham Lincoln as president. And so what we're doing is we're denying the consequent, and then from there we are inferring that the antecedent is false. Basically, if we were to define a modus tollens, we're going to say it's a logically valid form of argument which begins with the conditional but then denies that the consequent is true and ends with the conclusion that the antecedent is false. So you can say if P, then Q, not Q, therefore not P. The reason why this argument follows is that in the first premise, we've stated that if P is true, we know for a fact that Q is true, right? So P, and if P is true, then necessarily Q is true, meaning that there isn't any way in which Q is true, but then P is not true. So if you know that Q is true, from there you can say that P is, I'm sorry, if you know that Q is not true, right? Since P entails Q is true, that means in any scenario in which Q is true, we can just know that P is true. And so if we eliminate Q being true, we can also eliminate P being true. And once again, you can replace P and Q with anything. So now, related to this is what is called the contrapositive. And so you can derive, let's say you have if P, then Q. From this, you can derive that Q is false entails P is false. So this is just going to be modus tollens, or it's going to be a different way of stating the same underlying principle. So if like you have a conditional where P entails Q, it would follow that Q being false, that is the negation of Q, would also entail that the negation of P is true. So if you have P, then Q, then you could derive if Q is not true, then P is not true. So like, for example, you could say if it was raining, then my porch would be wet. And then from there, you can derive if my porch isn't wet, then it didn't rain. Now, another valid form of argument would be something which is called a disjunctive syllogism. So, for example, we can argue that either John is on team blue or on team red. John is not on team red, so John is not on team blue. So the argument begins with a statement, then rules out one of the propositions in the or statement, and then concludes by saying that the other proposition is true. So what you have would be a disjunctive statement, and then you negate one of the propositions in the disjunctive, and then you conclude by affirming the other proposition. So let's say you have P or Q, not Q, therefore P. So once again, a disjunctive statement is just going to be something which is basically an or statement. So if you have P or Q, that statement is going to be a disjunctive. And the reason why this works is because in an or statement, we're saying that at least one of the two statements is true. However, since one of them must be true, both of them cannot be false. But if we found out that in some or statement, one of the propositions was false, then it would be the case that if the other proposition was also false, then both of the propositions would be false. But this cannot be the case as was shown above, given how or statements was defined. So if we found out that one of the propositions was false, then the other must be true necessarily. So we can basically summarize this as P or Q, P is not true, therefore Q is true, and vice versa. You can do P or Q, Q is not true, therefore P is true. So this argument is valid no matter what you substitute for P and Q. Now, another form of argument you can use is to go from a universal case to a particular claim. So for example, let's say all men are mortal, Socrates is a man, so Socrates is mortal. We're taking a universal claim about members of a category, that being men, and then showing that Socrates is within that category, and then from there deriving that the claim applies to Socrates via him being in that category, man. So you can summarize it as this: all F are G, X is F, so X is G, and we're gonna go more in depth into this when we get into first order logic, but for now, let's just leave it at this. Now, another example, I guess you could say, is that some F are G, no F are R, so some G are not R. I guess to first give an example, you could say that some philosophers are human, no philosophers are irrational, so some humans aren't irrational. So what we're first doing is we're basically saying that some members of a first category are members of the second category, and since the first and the third category are mutually exclusive, there must be some members of the second category that aren't part of the third category, given that the third category and first category are mutually exclusive. And that since there are members of the first category in the second, if we were to deny that there are members in the second category, not in the third, we would have to say that we would have a contradiction basically, because it would mean that there isn't overlap between categories 1 and 2, or there isn't any mutual exclusivity between categories 1 and 3. I'm sorry, 2 and 3. Both of these options have been denied and thus aren't possible in this hypothetical. Now, similar to this argument above, we can give all men are mortals, all mortals are temporal, so all men are temporal. One way to summarize this would be all F are G, all G are R, so all F are R. The idea is that everything in the first category is in the second, and since everything in the second category is in the third category, that would mean everything in the first category would also be in the third. The only way to deny this entailment would be to say that there is something in the first category that isn't in the third. However, to do this would either have to say that this thing isn't in the second category, or all things in the second category need not be in the third. The latter would result in a contradiction since we have already affirmed the opposite. And if we go with the former, then we would end up with another contradiction because if the thing isn't in the second category, then either it wouldn't be in the first category, which is another contradiction, as it was already established that it was, or we would have to say that everything in the first category is not in the second. Now, what we've seen here is that the way that I'm sort of testing the validity of these arguments is basically by looking if there's like some form of contradiction by accepting the premises but then rejecting the conclusions. So, like for example, if I say if P then Q, P therefore Q, if I were to accept those two premises and then reject the conclusion, that would result in some logical contradiction. That's how I basically managed to prove the validity of the argument and reject the claim that that argument is a non sequitur. So it seems that the easiest way to prove an argument is valid is by simply saying that, is there a contradiction by accepting these premises but then rejecting the conclusion? Well, if there's a contradiction, then the argument is probably valid. If there's not a contradiction, then you know that the argument is not valid. Now, as said before, not all types of arguments are valid. So let's take these three ones, right? So you have non sequitur, which would be conclusion doesn't follow from the reasoning, that being the premise is given, and a logically invalid argument will be arguments where the conclusion doesn't follow from the premises. So non sequiturs and logically invalid arguments would most of the time basically be the same thing, whereas logically valid arguments would be the opposite, where the conclusion does follow from the premises. So here's an example of an invalid argument. Some things on earth are men. Some things on earth have 8 legs. Therefore, men have 8 legs. Now, clearly, there's, humans on earth, right? And I don't know, there's spiders on earth which have 8 legs. These two things are not overlapping categories. So clearly, we know this conclusion is false. And so, therefore, since we know that obviously the two premises are true, somewhere in this argument, we've given an invalid inference. That being, we have an invalid deduction. And the reason why is that although the first two premises are true, there's no reason to suggest that the two categories we've given, that being men and 8 legged creatures, are overlapping. Like, no premise exists in this argument which suggests that, and it's not like self evident or anything like that. And so, because of that, we can't conclude that therefore some men have 8 legs because there's no premise stating that there's a overlap between these two categories. Now, before I basically gave examples of what a valid structure would be like, right? So, for example, you have modus ponens, modus tollens, and so forth, right? But there's also like common examples of non sequitur arguments that are, I guess you could say, in a way, they mirror the valid forms of arguments. So, the first one would be affirming the consequence. So, in here, you assert a conditional. Remember, a conditional is something like if P then Q, and then you assert that since the consequent is true, the antecedent is also true. So if you say if P then Q, Q is true, therefore P is true, that would be affirming the consequent. So a concrete example of this would be like, if John is a professional sprinter, then John has 2 legs. John has 2 legs, therefore he's a sprinter. Clearly, this argument is invalid. It's a non sequitur. And the reason why is basically that you're assuming that the only way in which Q can be true is if P can be true, meaning that you're saying that Q in some way has P as a necessary prerequisite, but that's never justified in the argument, and this is why the argument is invalid. It fails. Now, the reason why understanding these structures, basically, for example, with invalid arguments, which we're going to get into more structures of invalid arguments later on, is basically that these types of arguments come up like very often in debates where people will just put out a like blatantly fallacious argument, and if you just know the general structure of how invalid arguments works and how, for example, affirming the consequent, what it is, how it works, and how to detect it, it becomes very easy to just pick it up on the fly and then just call out your opponent for basically being a sophist and giving non sequitur arguments. Now, to go back to logically valid arguments really quick, whenever you have a valid deduction, right? So, for example, if you have if P then Q, P is true, therefore Q is true, the deduction there is going to be the third premise where you're deducing that Q is true. And here it follows, the deduction here follows a inference rule. And that one's going to just be modus ponens, which is going to be covered again down below. For some preliminaries, we're just going to simplify P is not true to not P from now on, so I don't have to say the entire thing. And then we're going to simplify if P then Q to just P entails Q. Now, firstly, we can give some inference rules here. So modus ponens, obviously we mentioned this before, P entails Q and P both entail Q. So if you have both of those two premises, you can derive Q. And this works for whatever you want to substitute for P and Q. Now, modus tollens would be given P entails Q and not Q, we can derive P. We can derive not P. So I already covered this before, so I'm not going to go into it again. Same with contrapositive. Now, here are some more inference rules. Now, firstly, we have from falsehood, anything follows. And what this means is basically the principle of explosion. So, like, let's say you have a contradiction. So, earlier, a contradiction was defined as basically two mutually exclusive statements. Like, if you have some proposition P and another proposition not P, well, I guess that would just be affirming and negating a proposition, but you get what I mean. If you have that proposition both being negated and affirmed, that's going to be a contradiction. And this principle is just that if you have that type of contradiction being true, you can derive any conclusion. So, for example, if I have P and not P, I can derive that unicorns exist, I can derive that turtles have 8 legs, and so forth. And that might sound a little weird at first, but when we get into propositional logic, you'll see why that follows. Now, another type of inference rule would be reductio ad absurdum. So let's say you take some proposition P and then you show that it entails like a contradiction, right? You can negate that proposition P. So if you say that if turtles have 8 legs, I wouldn't see 4-legged turtles, right? Let's say you want to prove that, right? So, or I'm sorry, you want to prove that turtles have 4 legs, and you want to use that type of argument. So you could say, suppose for a second that turtles had 8 legs. Then I would not see turtles with 4 legs. Well, I do see turtles with 4 legs. So clearly this is a contradiction, and so I can negate the initial assumption. Now, another inference rule is going to be and introduction. So let's say you have two propositions, P and Q. So let's say you want to say turtles are green and pandas have fur, right? So that's going to be your P and Q. From there, we can just introduce an and statement. Now, in an and statement, both sides of the statement are going to be true. So, like, let's say you have P and Q, right? You're going to be saying that both of those statements are true. So, if you know that both statements are true, you can make an and statement. Likewise, if you have an and statement, let's say R and Q, you can derive any one of those propositions. So, if you know R and Q is true, you can derive that R is true, and you can derive that Q is true. And this is just because of how an and statement works. Once again, if you have an and statement, it's just going to be that both sides of the connective are true. And if you know that both sides are true, obviously one of them is true, and you can derive either one. Now, we have or introduction, which is somewhat similar to and introduction. However, with an or statement, which we earlier defined as a disjunctive statement, if you take like a proposition P, right? If that proposition is true, you can say P or Q is true, where Q is a substitute for anything, simply because in a disjunctive statement, only one of the propositions has to be true. So you can have one true proposition and one false proposition in a disjunctive statement, and the entire disjunctive statement would be true because of how it's defined. So, like, let's say I said zebras are real or unicorns are real. Even though unicorns aren't real, the disjunctive statement itself is true because only one of those statements has to be true. So all you're really saying is that one of these propositions is true in the disjunctive statement. Now, the sixth inference rule we're going to cover here would be or elimination. So let's say you have an or statement. Then if we demonstrate that either side of the connective entails something, so for example, R, then we know that proposition is true. So let's say you have P or Q, and you know P entails R and that Q entails R, since we know that both propositions entail R and that one of those propositions is true, we can just say R is true. So if I had to give an example of this, right? So let's say if the Lord of the Rings exists, then books exist because obviously the Lord of the Rings is a book, right? So if it exists, then there is a book out there. Similarly, if Harry Potter exists, then a book also exists because that's another book. So you can say either Harry Potter exists or the Lord of the Rings exists. If Harry Potter exists, then books exist. If Lord of the Rings exists, then books exist. And so from that, you can derive that books exist since you have a disjunctive statement. And then you know that each side of that disjunct entail a conclusion. And since both sides entail that, and since we know one of them is true, we can just say that the conclusion is true. Now, the seventh one we're going to cover would be double negation. So, negating a proposition twice is the same as affirming it. Remember, so if you have like a proposition like P, that's just going to be a declaration of some truth claims. Let's say turtles are real. So, that's going to be a proposition. So, if you have not P, let's say P just represents turtles are real. If you have not P, you're just negating that statement. But then if you have not P, that being a double negation, you're back to affirming that statement. So not P is false is the same thing as P is true. Now, above, we've so far covered what a logically valid argument is, right? So a conclusion that is accurately derived from its premises and not just a non sequitur. However, logical validity isn't the same thing as soundness. Now, soundness refers to an argument actually having true premises and a valid deduction. So let's take a look at this argument, right? If birds are green, then the sky is blue. Premise two, birds are green, therefore the sky is blue. Now, the argument is logically valid, but the second premise, I'm sorry, if the first premise is false, and thus the argument is unsound. Now, this is despite the fact that the conclusion is true, because in order for an argument to be logically sound, all of the premises have to be true, and then the conclusion has to actually follow from the premises. So in this case, premise one is false. And this is just because like there's nothing about birds being green that entails that the sky is blue. So you can't really prove it. So once again, we can define logical soundness as just occurring when an argument is logically valid and the premises used to derive the conclusion are actually true. Now, let's take an actually logically sound and logically valid argument. So, premise one, if the USA began in 1776, then it didn't exist in 500 BC. Premise two, the USA began in 1776. Conclusion, therefore, the USA didn't exist in 500 BC. Now, premises one and two are true, and they entail three. Hence, three follows and is true. So, this is a logically sound argument, and it's also logically valid. Now, to explain further, logically valid arguments are once again going to be ones where the conclusion follows from the premises, and logically sound arguments are just going to be logically valid arguments which actually have true premises. So in a way, logically sound arguments are just going to be like a subset of logically valid arguments. Now, one more thing to cover, right, before we get into, I believe, logical fallacies are next. Yes. So one thing to cover before we get there is that whenever you analyze an argument, you would have to typically it's best to try to break it up into different steps. So let's take this one. Socrates is mortal because he's a man. I gave this argument before, right? And we said the logician's job is to analyze whether this is valid. And the best way to do this, in my opinion, is to try and break it up, right? So you can break it up into these two steps. You can say one, Socrates is mortal. Two, because he is a man. So you've broken it up right there into two. Then you can say Socrates is a man, therefore Socrates is mortal. Because remember, usually we're going to put the conclusion below underneath the premises, and we're going to have the premises stated first, and then we're going to have the conclusion derived from the premises. So we're just fixing the argument basically into something we can analyze better. Then what you'll notice is that in this argument that Socrates is mortal because he is a man, although this isn't stated directly, there's I guess you could say, a hidden premise. The premise that all men are mortal. Now, this premise that all men are mortal, it's going to be something in like the background knowledge of the person making the argument, and it's going to be implied in their statement, even if it's not directly stated. And this is important because a lot of arguments that you see are going to have hidden assumptions and hidden premises within their, like basically just within them. Now, sometimes you can excuse it, right? Like, for example, with this argument, the premise that all men are mortal is something that most people take to be obvious, and so, it's understandable that someone doesn't want to directly state it, right? It's kind of like stating the sky is blue for them. But when you actually analyze the argument in like a rigorous way, you're going to want to include any hidden assumptions or any background claims that this person has to actually analyze the validity. Now, once we've broken this claim, this argument up into these different steps, right? Socrates is a man, all men are mortal, therefore Socrates is mortal. Now we can look at the inference there, and we can see that yeah, this inference is valid. So the argument is logically valid once we include that hidden premise, right? But if you weren't to include it, then it wouldn't be valid. But I think it's fair to include it, even though it's not directly stated, given that once again this is just going to be implied in the statement given the background knowledge of the person making the argument. So now we can finally get to logical fallacies. So we actually covered this earlier when we talked about invalid arguments. But basically, when you like try to break down an argument step by step into a chain of premises, you're going to see that sometimes they have invalid inferences. And we've already covered some of these, such as affirming the consequent. Now, we can give a specific name to these now, that being these are fallacious arguments, or as I said before, they're non sequitur arguments. So here's affirming the consequent once more. We have P entails Q. Q is true, therefore P is true. And earlier I said that a lot of fallacious arguments, in a way, mirror logically valid arguments. And in this case, the structure of this argument is very similar to modus ponens. And in modus ponens, right, we have the first premise is a conditional, the second premise has the antecedent of that conditional being affirmed, and then the conclusion ends with the consequent being affirmed. But the difference here is that the first premise, although it is a conditional, in the second premise, instead of having the antecedent, we now replace the antecedent with the consequent. So remember, in this case, the antecedent is P and the consequent is Q. And in the second premise, rather than affirming the antecedent, we have now affirmed the consequent. And this is why it's logically fallacious. There's nothing in the conditional that I've given that says that if Q is true, P is true, right? That's just not there. So saying Q is true is irrelevant to trying to determine the truthfulness of P. And this is why, obviously, it's called affirming the consequent, because in the second premise, that's what you're doing. You're affirming the consequent of the conditional. Now, another example of a fallacious argument is going to be what is called denying the antecedent, right? So let's take this argument. If John is a boxer, then he has two hands. Two, John is not a boxer. So John does not have two hands. So in this argument, you have P entails Q, not P, therefore not Q. And this is going to be pretty similar to a modus tollens. So if you look at the two, right? So in the first one, you have P entails Q, not P. But then in the second one, you have P entails Q, not Q, right? So in modus tollens, you have a logically valid argument because we've established that if we can prove that if that P is true, then Q is true, right? So P and Q go together in a way, right? So if P is true, then Q has to be true. And so if we can conclude that Q is not true, then we can conclude that P is also not true. That's valid. However, in a denying the antecedent argument, right, you do not have that same inference rule. Instead, you have the conditional, you have the negation of the antecedent, and then a negation of the consequent. And to like try to explain where this argument sort of went wrong, right? Is that whenever we use denying the antecedent, we first have a conditional, then we deny the antecedent, and then we deny the consequent. However, the conditional never states that the consequent cannot be true without the antecedent. It just states that the antecedent entails the consequent. So the conditional above never stated that John can only have two hands if he was a boxer. It just stated that being a boxer means having two hands. So if we go back to the original argument, right? This argument, if John is a boxer, then he has two hands. John is not a boxer, so John does not have two hands, right? This argument never states that John can only have two hands if he's a boxer, right? It just says that being a boxer implies having two hands. It doesn't tell you whether or not you can have two hands without being a boxer. And this is where this argument fails. And that's basically why it's a non sequitur. Okay, so now we can move on to affirming the disjunction. And once again, this is going to be sort of a mirror to a disjunctive syllogism, which is valid. So let's take this. John is a human or John is a man? Premise 2, John is a human, so John isn't a man. Now, the failure of this argument would basically be that you're assuming that being human and being a man are mutually exclusive when the first premise doesn't state that. So, what you have to remember is that in an or connective, right, it just means that at least one of the propositions is true. It doesn't state that only one has to be true. It just states that at least one is true. Now, you can like sort of try to salvage an argument like this, right? And that's by actually establishing exclusivity, right? So if you say John is human or John is a fish, 2, John is not both a human and a fish, 3, John is human, therefore John is not a fish, right? So you've actually established exclusivity in this argument being shown here. So this argument, it's valid, right? Because I've actually established that there's an exclusivity between being a human and being a fish. And so therefore the conclusion actually follows. Now, what we've covered above, right, would be examples of formal fallacies. However, although we have plenty of examples of formal fallacies, we also have like a ton of informal fallacies. Now, the difference, in my opinion, can sometimes be arbitrary, but usually a formal fallacy is going to be like an issue with the argument structure itself, right? And whereas with informal fallacies, it's not always the case, but I think sometimes you can make the argument that it is the case. Now, to give the first example of this, an equivocation is basically when you shift the meaning of a term, right? So let's go through this example. Socrates is Greek. Greek is a language. Therefore, Socrates is a language. Now, here, this argument is invalid because we've used Greek in one way here, and then we've used Greek in another way in the second premise. And so, therefore, the conclusion doesn't follow. Because, as said before, the way Greek is being used is in two different senses. And since you're using Greek in different senses, you can't make any inference there. So it'd be like saying Socrates is F, G is a language, therefore Socrates is a language. Since F and G are different, there's no inference there. Now, a second informal fallacy we can go over is something which is called begging the question. And begging the question is just assuming your conclusion in the premises. Now, remember, the point of a set of premises is going to be to prove some conclusion. Now, if you're just going to assume the conclusion in the premises, then you're just giving a circular argument, right? You're trying to prove the conclusion by first assuming the conclusion. It's like, let's say someone does this. 1, atheism is true. 2, so God isn't real. Now, technically speaking, right, atheism being true does entail that God isn't real. It's just that you're giving it tautology, and so this isn't really like a good argument. It's just you're begging the question. You're using a circular argument. So technically, you could say the argument is logically valid because premise 1 does entail the second statement. It's just that premise 1 is the same statement as the second statement. They both have the same underlying proposition, and so there's not really an argument here besides just saying atheism is true because atheism is true. You're just begging the question. Now, another example would just be giving a false dilemma. Now, technically speaking, this doesn't have to be invalid. People can give false dilemmas without having an invalid argument. So, for example, right, if I say Joe is either a doctor or a father, Joe is not a father and doctor, so there Joe is not a doctor, thus Joe is a father, right? So the second premise establishes a false dilemma. Now, this argument itself, it's logically valid, but it's not logically sound because premise 2 is false, right? It establishes a false dilemma. Now, fourth, we can give appeal to ignorance. And this just occurs when someone assumes that a proposition, because it has not been proven true or false, that therefore you can conclude that it's the others. Like if it hasn't been proven true, then we can conclude that it's false and vice versa. So if you have P has not been proven false, so therefore P is not false. That's a non sequitur. Same thing with P has not been proven true, so P is not true. And the reason why is there's just no valid deduction here. There's no reason to suggest that something not being proven true entails that it's not true. I mean, for example, right? if there's like some proposition that we just don't know, maybe it's like a new scientific discovery, that proposition is still true even before we know it, even before we have a proof of it. And so therefore, like, clearly something doesn't have to be proven true to be true. Now next we can cover the fallacy of composition. Now basically this assumes that when like something is true of a part, it is therefore true of a whole. So let's say cells are not visible to the naked eye. That's true. Humans are composed of cells. Also true. So humans are not visible to the naked eye. That's false because you're assuming that because cells are part of something, that therefore the whole has the same properties. Wholes do not have to have the same properties as their parts. Now, similarly to the fallacy of composition, we have the fallacy of division, which is kind of like the reverse, right? So if you say that like something is true of the parts because it's true of the wholes, then you're just committing a fallacy of division. So like let's say I want to say my wall is red, the blue spot of paint on my wall is part of the wall, therefore the blue spot is also red. Now, finally, we can cover ad hominem, which is just attacking the character of the person rather than attacking the argument. And I shouldn't really have to explain much there. That should be obvious. What I covered before would be like the introductory material for like, I guess you could say this is more informal, right? Whereas with propositional logic, we start getting more into like actually symbolizing logic and basically trying to formalize it. So first, we can basically define some symbols. And the reason why is that in propositional logic, we don't really have natural language. It's like natural language is going to be like a statement like Socrates is a man, all men are mortal, therefore Socrates is mortal, right? That's going to be a statement in natural language. Whereas we're trying to basically systematize and formalize logic into a very clear system. And that like propositional logic is going to be the first step to do that, basically. So first, we can define the logical conjunction symbol. So this symbol is just going to look like the upward facing arrow, right? And basically, this represents the and connective. So if you've ever had experience with Java, you're going to use two ampersands to represent this. But in logic, we usually use that conjunction symbol. So if you place the conjunction symbol between P and Q, that's the same thing as saying P and Q, right? Now, similarly, you have the disjunction symbol, which represents the or connective, right? So if you have P or Q, you're going to put the disjunction symbol between the two statements. And in Java, you use the two straight lines. Now, the negation symbol just refers to not. And in Java, we use the exclamation point, right? So this is just saying that, like, if you have a proposition P and you want to negate it, you would put negation P, right? That's all that. That's all that is. It's pretty simple. Now, the double-headed arrow is just going to refer to if and only if. So if you want to say P is true, if and only if Q is true, then you would say P double-headed arrow Q. That's how you would like write it out, basically, right? So you're saying that both sides of that connective, and remember, the connective just is the thing in the middle, right? So, or I guess same thing in the middle, but like it's the thing that sort of combines the two, right? So if you have the and symbol, right? If you have P and Q, the connective is going to be the thing in between. And likewise, in this case, the connective between P is true if and only if Q is true. The connective is going to be the double-headed arrow, right? What's going to represent it. And all that really means is just that both sides of the connective entail each other. So if P is true, you can infer that Q is true, and if Q is true, you can infer that P is true. Meaning that they're like a set that goes together, basically, in a way. So that you can't have one being true without the other being true. Now, likewise, the right-facing arrow statement just means entails. And in Java, we usually use if statements. Like if you have if P, then Q, that's going to be represented with a right-headed arrow. So like so you would put like P, and then you would put the arrow symbol Q, and that would be if P, then Q. Now, finally, we have the therefore symbol, and this just refers to therefore. So like if you looked at the arguments we did before, we had premise one, premise two, therefore, then we had some conclusion. You would just replace therefore with the symbol. And similarly, you have a double turnstile, which just represents the same thing, basically. Now, the reason why this is useful is that we can like simplify a bunch of arguments. So let's take this one. If John is a philosopher, then he thinks. John is a philosopher, so he thinks. We did this before, but now we can basically simplify this into what is essentially like just a couple of characters. So you're going to take the first premise and you're just going to use P, then you're going to have the arrow, then T. So P in this case represents John as a philosopher, T represents John thinks. So you're going to have P, therefore T. And then the second premise, you're just going to affirm P. Once again, P just means John is a philosopher. And then the conclusion, you're just going to have therefore T. Now, we've only used a couple of characters to represent this argument, which before would have taken up a lot of space. And this is part of the usefulness of having propositional logic. You can just represent propositions with just one character, basically, and then you can have the connectives also be represented as one character. It helps you simplify and systematize a lot of arguments a lot better. Now, I should note, right, in this case, it's pretty obvious what each of the symbols refers to, right? So it's obvious to know what P refers to and what T refers to. One of the reasons being that I defined it. It's just that, like, in a lot of times, right, people will just not define their terms and they won't define what each character means. And that's not only is it annoying, but usually it's a shield for sophistry because, like, if you define what the terms mean, then anyone can just see, yeah, this is a non sequitur. So if you see an argument and the person doesn't define what each term means, then just call them out about it. They're probably hiding something, if you want me to be honest. Now, earlier, right, I mentioned EFQ. Now, given what I've said about propositional logic and how basically it helps us sort of formalize arguments and it helps us remove any ambiguity since every proposition is represented by a letter, right? So if you have the proposition John is a human, that's just going to be represented by one letter. And anytime you want to repeat that proposition, you would just say it again. What you can do, right, is this gives you the ability to basically systematize arguments. And as I said before, we have the principle of explosion. And I said that we can basically do that once we get into propositional logic and show how that's true. So let's make a proof for this. So if you let P represent the proposition which is negated and affirmed, right? So let's say, so in the principle of explosion, we said that if you have a contradiction, that being P and not P, then you're going to have every proposition being true. So in this case, let's just say P is an arbitrary letter that just represents any contradiction, right? Remember, this is a reductio argument, basically. We're assuming that there's a contradiction and showing how this leads to an absurdity. So let's start with this. So the first premise is assumed for reductio, right? So the first premise just states that there's a contradiction. Now, the second point here is a deduction. And we've derived that P is true from the first premise via and elimination. Remember, we said that an and statement just means that both propositions are true and that you can derive either one from an and statement. So we can derive that P is true from P and not P because it's part of the first statement. So we can deduce P is true via and elimination. Now, third, we can say that P or Q is true, right? That's a disjunctive statement. Now, remember, we can do this through or introduction because we've already stated that an or statement is just something that has one, it's just going to be a statement where one side of the connective is true or both sides are true. So since we know P is true, therefore it follows that statement P or Q is true simply by the fact that we know that one of those statements is true. So because we know P is true, we can conclude that P or Q is true via or introduction. Now, we can once more derive that not P is true via and elimination, which is going to be similar to how we derive that P is true, right? It's the same concept, basically. Because we know that both sides of the connective are true, we can derive that the statement not P is true, since that's part of the connective. However, we can now derive that Q is true. The reason why we can derive that Q is true is that we know from 3 that P or Q is true, right? We've derived that. And we know from 4 that P not P is true, and we've also derived that. However, via disjunctive syllogism, we can derive that Q is true. Now, to recall before, right? Since we know that in premise 3 we have a disjunctive statement, and in premise 4 we know that one of those statements in the disjunctive is negated, we can conclude that the other proposition is affirmed. So we've already covered the reasons for that before, so I'm not going to get into it again. But what this means is that we can derive Q is true from P and not P, right? And this is important because we can substitute Q for anything, right? So let's say you want to say Q means unicorns are real. we can substitute it and Q follows from the statement P and not P. And this is why we say from falsehood, anything follows, and why it's called the principle of explosion. If you assume a contradiction is true, it follows that every proposition is true. Now, although propositional logic is good, right? And it helps you formalize certain arguments that use propositions, it's not good enough. We needed something better. So let's take this. All men are mortal. Socrates is a man, therefore Socrates is mortal. And the first statement, we have a quantification. So we're saying something about an entire group of things, right? So we're saying something about a predicate, where man is a predicate, and we're saying everything that has that predicate also has the predicate mortal. And then we're saying in the second statement that there's a subject who satisfies the predicate, and then we're making a conclusion based off. So in order to go beyond propositional logic, we need a way to basically represent predicates, objects, and a way to quantify over objects. And this is where first order logic comes in. In first order logic, right, things are a little different because now you have a way to represent objects and predicates. Now, a predicate is just going to be a description or quality of a thing, right? So for example, if you have Socrates as a man, man is going to be the predicate there, and the object there is Socrates. An object is obviously just going to be the thing itself, which is not a predicate, but is instead predicated over. Now, in formal logic, objects are typically represented with a lowercase character called variables, whereas predicates are represented by uppercase characters. So let's take this, right? Suppose we want to formalize Socrates as human. We begin by defining our variables to represent an object. So S means Socrates. Then we can define our predicate where H means human. So you could say H, and then after H, you would say S. And what this means, right, is S is AH, which if you translate it using our definitions of S and H, you would just mean Socrates is human. Likewise, F and then X just means X is F. So F is being predicated to the object F. And if you have a definition of F and a definition of X, you're going to be able to translate it just fine. But this only solves one of our issues because, once again, we have to also quantify over objects, not just predicate over them. So before, right, we said all men are mortal, right? How are you going to represent that? Well, first order logic gives you a solution for that as well. And this is because we have quantifiers. And these are going to be basically new symbols that we can introduce to help us, right? So let's start first with the universal quantifier. So this is going to look like an upside down A almost, right? And this can be translated as for every or all or something like that, right? So for example, if I said universal quantifier X, then I put f of X in like parentheses, I would be saying for every X, X is F. And if I wanted to say all men are mortal, I could write it as universal quantifier X. Then I would put HX entails MX. So you would be saying for all X, if X is H, then X is M. And this would, once again, this would be translated, given our definitions, as for every X, if X is human, then X is mortal, which in turn means everything which is human is immortal, which just means all men are mortal. So we've translated our original phrase in natural language into first order logic. Now, second, we can go over the existential quantifier, which just looks like the backwards capital E. And this just means roughly there exists or there exists some. So let's say I added an existential quantifier in front of the letter X, and then in parentheses I added the capital F in front of a lowercase x. I would be saying there exists some X such that this X is F, right? Now let's say F means cake, right? Then I would roughly be saying there exists some X such that X is a cake, which in turn just means there exists something that is a cake, which is simplified to there is a cake. Now, finally, we can add a equal sign and a not equal sign. So, like, if we wanted to say that two objects are identical, we can use the equal sign and vice versa. Now that we have more symbols to work with and quantifiers to work with, we can also introduce 4 new inference rules. So, firstly, we have universal instantiation. So, if you go back to our example of Socrates as human, right? We have H being predicated to S. In that case, H is a universal, S is a particular thing. So universal instantiation is just going to be involve predicates basically. So let's give a concrete example of this. Let's say you have for all x, g of x entails ox, right? Now from this you can derive gj entails oj. Right. So let's take this, right? Let's say we define G as God and O as omnipotent, and then we define the variable J as Jesus. Then what you're basically saying is that anything which is God is omnipotent. So if Jesus is God, he is omnipotent, right? So this is going to be a valid deduction. Basically, if you have a quantifier, you can just insert any variable there. Now, second, we're going to have existential introduction, basically. So from a specific instance, we can make a quantification. You can use an existential quantification basically. So basically, right? Let's say that you have f is predicated to a, right? From there, we can infer there exists some x such that x is f, right? So let's say in natural language, we write if Arnold is furry, then something exists that is furry. In this instance, we would be using existential introduction, right? So third, we have universal generalization. And that just means that we can infer a universal quantification from a specific instance, given, and this is important, given that the specific instance is arbitrary. For example, let's say that we introduce C as a fresh variable that isn't used prior. And this is important. It has to be a fresh variable that isn't used prior. And we just know that P is true of C, not because of any prior premise or presupposition, but just in virtue of C existing, right? Then we can generalize this and say for all x, P is true of x, right? Or x is P. There is one other inference rule. We can use existential instantiation as well. So let's say you have an existential quantifier. You can derive an instance via a new variable. So let's say you have there exists some x such that x is f. You can derive C as f, where C is a new variable not used elsewhere. And that's important because you can't use a variable that's used elsewhere in your argument. It has to be a new, fresh variable, right? So, like, let's say you have A is G, there exists some X such that X is F, so therefore A is F. That's invalid, and you cannot use existential instantiation there because A is already used elsewhere in the argument. The variable has to be fresh, basically. So now that we've defined inference rules and the new symbols, we've actually solved our problems with propositional logic. Because now we can basically translate arguments about both subjects and predicates and just using simple propositions. So let's say we have all men are mortal, Socrates is a man, so Socrates is mortal. Basically, we can take the first statement, right? So all men are mortal, and we can formalize that to for all x, if x is h, then x is m. Right? And we've defined all these terms below. So H just means man, M means mortal, and S means Socrates. So we can now formalize all men are mortal into the first statement on the right. Then we can take the second statement and we can say that just means S is H, which we've represented on the right. And then we can take the conclusion and just say S is M. So here we've basically in a way formalize the first argument that I've given. Now, what's it called? Here's, I guess you could say, a hidden inference step in it, right? So if we look above, right, in the original argument, we have all men are mortal, Socrates is a man, so Socrates is mortal. Why does this follow? So first, right, we can say that from universal instantiation, we can say that the first premise, that being for all x, x is h, therefore m, x is m, we can derive from that that if s is h, that therefore s is m. And once again, this follows from universal instantiation because you're just substituting x with s, and therefore it's valid. Now, we can use this alongside premise 2 to derive that s is m. So this is just going to be a modus ponens argument because you have the conditional, if s is h, then s is m, and then you have the antecedent affirmed, that being if s is h, and then from there you have the consequent affirmed. So we've shown that this argument is logically valid and that the reason why it follows is through universal instantiation and through modus ponens. So basically, through first order logic, we've managed to formalize a very simple argument. And although this argument is simple, right, you can use this basically for any argument, with a few exceptions, obviously. And we're going to get into that later. Now let's move into a different argument. So let's say some elephants are pink. All pink things are bright. So some elephants are bright. Now we can translate this by first defining our variables. So let's let E refer to elephant. So if you're saying E is predicated to X, you just mean X is an elephant. Likewise, P means pink, so X is P just means X is pink, and X is B means X is bright. Basically, right, we're gonna, when we analyze this, we can use existential instantiation, universal instantiation, and elimination, modus ponens, and introduction, and then finally existential introduction to show that this is valid. And it's gonna be, I guess you could say, a somewhat long process, but it'll show that we can prove rigorously that this argument is valid. So first, right, let's take premise one, that some elephants are pink, which we formalized on the right. Now, from premise one, the statement that there exists something which is E and P, we can derive that C is E and C is P, where C is an arbitrary and fresh variable, and this follows because of existential instantiation, which we covered above. Remember, from an existential quantifier, you can derive a specific instance given that the variable you're using is fresh. It's new and it's not like used elsewhere. Since we haven't used C elsewhere to denote anything, it's fine if we use it here. Now, from premise two, the statement that for all X, if X is pink, then X is bright, we can derive that if C is pink, then C is bright. Remember, this is universal instantiation. However, we have stated that C is an elephant and that C is pink. And given and elimination, remember, if you have an and statement, right, both sides of the connective are true. So you can derive that C is pink from the and statement. So we've derived that via and elimination. However, we can derive that C is B given modus ponens, right? So earlier we figured out that C is pink, right? Then we knew that if C is pink, then C is bright. So now that we have those two statements, those two propositions, we can therefore derive that C is bright given modus ponens. Now, since we know that C is E and C is B, we can say that C is E and C is B via and introduction. Remember, if you know two propositions are true, you can get the and connective and you can connect them together with that. So now you have C is E and C is B, right? However, once again, since we've defined the inference rule of existential introduction, we can say that since we know C is E and C is B, it follows that there exists some X such that X is E and X is B. And that is basically what our initial conclusion was, and thus we've shown that this argument is logically valid. Now, we've proven this argument is valid, but you're probably going to notice that that took a lot of steps, more than it should have, given that the argument initially was intuitively, like, it's logically valid and we can just know that intuitively. So you might just be asking, like, what's the point of doing all that work? Well, in a way, right? It's the logical equivalent of proving like that 1 + 1 = true. Like, it might be useless on the surface, but learning how to do it is going to help you prove that certain more complicated arguments are logically valid, or if they're logically invalid. So basically testing it out on these types, like testing out the inference rules on like these types of arguments, which are easy, is just going to help you understand how to do it on arguments that are way harder to comprehend. So here what we've done is we've basically just used first order logic to prove an argument is valid, like using the inference rules, but we can also use it to prove that arguments are invalid, right? So let's take this. Socrates is Greek. Greek is a language, therefore Socrates is a language. If you try to formalize this, you're going to get S as G, where G is a predicate meaning Greek and S is a variable meaning Socrates. L is predicated to G, where G is the language Greek. Therefore, what you've seen is that we're using Greek in two different senses once you try and formalize it. In one sense, Greek is a predicate denoting ethnicity. In the second sense, Greek is an object which is predicated over. So it's using Greek in two completely different senses, basically. And so because of this, right, it's a clear non sequitur. To step back a bit, we can like add more to our understanding of predicates. Now, this is because first order logic also covers that which is called two-place or relational predicates. So let's say you want to say John is the father of Mark. You could use a one-place predicate father and do P is predicated to J or J is P, right? Now, you could also do something else, right? Let's say you want to use a different variable, right? Maybe you want to say Mark is the father and so forth, right? Now, usually that'll be fine. But the issue is right, we've just said that John is a father. We've not said who John is a father of. Furthermore, suppose we wanted to say John is the father of Alex and John is not the father of Luke, you would have to come up with a new predicate for each person, basically, right? So you would have to say maybe like F of J, where F means father of Luke, and then P of J means John is the father of Alex, right? So you have two different predicates for each sentence. But let's say you only want to use one predicate because obviously coming up with that many predicates is eventually just going to be annoying to do. What you can use instead are relational predicates, right? So, for example, let's say you want to do a two-place one. So you can say fatherhood, right? So you can say F refers to fatherhood, and you can do F, and then in the parentheses, you have X separated by a comma Y. Now, in this statement, right, you're saying that X is the father of Y. And this is why it's called the two-place or relational predicate. If you want to say John is the father of Mark, right, you could say F, J, comma, M. And this is going to be a relational predicate saying John is the father of Mark. Likewise, if you want to say John is the father of Alex, you can say F and then in the parentheses J, comma A. Now, we can take this further by having three-place predicates as well. And you can like continue this on and on. So let's say you want to say the road is in between the McDonald's and the Burger King. So you can say I and then in the parentheses R, comma M, comma B, right? So that's one way to write it. And you can say let I mean X is in between Y and Z, and then R means road, M means McDonald's, and B means Burger King, right? So here what you have is a relational predicate. You're describing how R relates to M and B. That being R is in between M and B given how you've defined it. So like so far, right? First order logic basically allows you to predicate over objects, to quantify over objects, and to describe the relations between objects, right? But let's take this statement. The Ford is red, right? That's pretty easy to formalize. All you have to do is RF. That's it. It doesn't take much else. But let's say you wanted to say that red is a color and the Ford is red. Well, that doesn't make too much sense because, well, if you try to use first order logic, you're going to have to say that R is a object. But that means you would have to equivocate on R, meaning that in the statement, the Ford is red and red is a color, you're actually equivocating on the term red, which doesn't seem to make much sense intuitively at all. Now, one way to fix this is if you just predicate over the object over the predicate. So instead of having a lowercase r to describe a first order object, you now have a uppercase r to describe the predicate, and you're just predicating over the predicate, right? So red is a color, it's just capital C and then capital R, representing R is C, where R and C are both predicates. It's just that now you're predicating over a predicate. And this is important because now you're basically predicating over other predicates. And this is what is called second order logic, right? In first order logic, you're only predicating over objects and you're only quantifying over objects, right? So if you wanted to say for all x, x is r, right? You can only do that where x is going to be an object. You can't have a predicate and a quantification in first order logic, and that's going to be one of its limitations. However, if you have second order logic, we're now no longer constrained by that, and we can now predicate over other predicates, right? So red is going to be a predicate, and you can say red is a color, where color is a second order predicate applying to the first order predicate. So we can divide up predicates into first order and second order, right? So second order predicates are going to be predicates of other first order predicates, and first order predicates are going to be predicates of objects. Now, as I said before, we can also quantify over predicates, right? So let's say you do for all F, C is F, and tells V of F, right? So let's say you want to say all colors are visible. you can represent visible as V, color as C, right? So you're going to say for all F, meaning for every predicate. If that predicate is a color, then it follows that predicate is visible, meaning its extensions are visible, right? Now, you might be wondering, right? Why not just use second order logic only? Why did I even bother with first order logic? Well, the reason why is basically that there's no complete and sound formal deductive system for second order logic. So it's incomplete. More work needs to be done. So although second order is good, first order is likely going to be sufficient for most arguments. Now, prior to this, right, we've only covered logical possibility and necessity like once, and that's with the laws of logic. So if you remember correctly, I said that like the laws of logic are typically understood to be just true necessarily. They're not contingent upon like it's not like there's some possible way in which the laws of logic could be true, right? Or I'm sorry, false. And we can actually use symbols to describe modality. Now, modality is just going to deal with possibility and necessity. And well, so for example, let's say if I wanted to say that Superman is possibly real, right? I would have to use terms about modality, right? Because I'm saying possibly. I'm not saying Superman is actually real. I'm just saying it's a possibility that he's real, right? So I'm saying in some possible scenario, Superman could be real. Now, in order to do that, right? In order to like formalize that, I would have to use what is called modal logic. Now, modal logic just deals with modality. And it should be important, right, to cover this up or to clarify it, is that whenever we speak about possibility and necessity and modal logic, we mean them in like a very specific sense, right? So when we say possible, we mean possible in the most strict sense possible. And when we say necessary, we mean necessary in like the most strict sense possible, right? And so, like, well, let's take this example given by Peter Smith. Let's say Joe jumped out of a 20th floor window without parachute, safety net, etc., and fell unimpeded onto a concrete pavement, so she was injured. Let's grant that the laws of nature are the way they are. There's no way in which the premises could be true and the conclusion false. Assume that we're talking here about on Earth, Joe is a human, and so forth, right? In the actual world, falling impeded onto a concrete from 20 floors up will always produce serious, very probably fatal injury. Does that make the inference from the premises to the conclusion valid? Therefore, can we say that necessarily because Joe jumped out of the window, she's injured? Well, no, because even if it's not physically possible according to the laws of nature, right? Because of how gravity works, there's still a possible scenario, right? We can still conceive of a situation where, let's say, the laws of nature were different, right? So we can say that maybe in some possible world, the laws of nature are different, and then so like Joe just falls down slowly like a feather and doesn't hit the floor like that. And so we're talking about possibility in this very loose sense. It's right. It's not going to be in like how we usually describe it, where if something is against the laws of nature, we just say it's impossible. No. We mean possibility in like this very broad sense when we speak about possibility. And likewise with necessity, we mean it like it is not possible in the sense that we use possible in modal logic for something to be false. That's what we mean by something is necessary. So to help explain how this works, right, we can introduce some symbols, right? So before with first order logic, we introduced some symbols to help us use it. Likewise with propositional logic. In modal logic, we can introduce these new tools to help us formalize modal statements, right? So let's start with the box. This is just, it's necessary that. So like if you wanted to say X is necessary, you would just write box, then X. Likewise, the diamond roughly means it is possible that. So, like, if I wanted to say it is possible that X is true, I would just say possible X, or diamond X. Now, given these symbols, I can write it is possible that a Kryptonian exists, right? So I can say possibly there exists an X such that X is K, where K means Kryptonian. Now, earlier we talked about the laws of logic, and using modal logic, we can formalize the laws of non-logic now. So we can say the law of identity just means necessarily P equals P, non-contradiction. It is not possible that P and not P. Law of excluded middle would just be necessarily P or not P. So here we've basically formalized the laws of logic using modal logic. And you can do a lot else with modal logic, but since this is just introductory, I'm probably going to leave it there. And these are the references, and I think that's about all I have for today.